People, hope we're doing well. This is the second video for the application of integral calculus to parametrics. When we left off after the first video, we had basically just found the arc length of the curve defined by these parametric equations over the intervals 0 to 2. Okay. Now, I do want to go ahead and show you the graph. That is basically the whole graph of x. So, see, it's t cubed and t squared. That's the whole graph. Now, if I just wanted to show, of course, just the portion that I needed to find the length of, I would just go 0 to 2 on my t min and t max, and I'll draw it again. And what we have here is we can go ahead and change the window. Let's do 0 to 10. And there we go. Okay. Now, we're just looking for that. Okay, and so you got to remember that this is 1, 2, 3, 4, 5, 6, 7, almost to 8 right here. So basically the fact that that's a little longer than 9 kind of makes sense. Okay, so let's go ahead and let's do it in terms of, rectangular. Now, I'm going to go ahead and quit out of here. I'm going to go to mode. I'm going to go down here to my function mode, and we'll get out of here. Now here it is, here's the integral that we did in the last one on our calculator. I've already put the x to the 2/3 in there, okay? Because remember that if x is equal to t cubed, that implies that t is equal to x to the 1/3, and therefore this y is equal to t squared becomes x to the 1/3 squared, or x to the 2/3. Okay? So we know what the function looks like here. Okay, so we have our function. We can, of course, go ahead and find dy dx. We're going to need it, right? And it's 2/3 x to the negative 1/3. We also need to redo our limits of integration, right? And I know that if t is between 0 and 2, then t cubed is between 0 and 8. So our limits of integration here are between 0 and 8. Alrighty, well, let's go ahead and set up the, set it up in rectangular. Remember, it's a to b of the square root of 1 plus dy dx squared dx. And in this case, that's 0 to 8 of the square root of, well, this is 2 over 3 x to the 1/3. So that's 1 plus 2 over 3 cube root of x, or x to the 1/3 squared dx. And of course, again, we can go ahead and do that all day long. But let's go ahead and use our calculator for this one again. And we're going to go and we're going to find our integral, and we're going to do it from 0 to 8. Now, I already have y2 as y1's derivative, so I'm going to go ahead and do it by shortcutting again. And I'm going to have y2 squared with respect to x, and that, that actually, there, it's supposed to be plus. Okay, and enter. It's taking a while to churn because it has to basically use this approximating algorithm as it runs through there. It also has to not only, it has to run it through y1 and y2, since y2 is defined in terms of y1. So that's why it's taking just a minute. Wow, this is really taking a long time. And there we go. And this was 9.068. Okay, well, that's not exactly the same, right? This is not the same as that. But remember, like I said, when your calculator does basically does an integral, especially when you have to sort of daisy chain it from y1 and then y2 is defined as y1's derivative, and then you're doing the integral on the main screen. The algorithm and it's basically an approximation algorithm. Well, are these approximately the same value? And the answer is yes, okay? So you can feel comforted. I mean, it's basically 5/1000ths of a unit off. So basically, since both of those were approximated, you can be pretty confident that that you've arrived at the correct answer. But I just wanted to verify this answer by doing it in a way that we're actually familiar with. Alrighty, let's do another one. Find the length of the curve over the given interval. Okay, let me zoom out just a smidge. Now, we can go ahead and let's go back to parametric on our calculator. And we can go ahead and, put radical t in here, and then put 3t minus 1 in here. And let's go back to the main screen. Now, what we have here, we need dx dt and dy dt. So dx dt, we know, is 1 over 2 root t. We've done that 100 times, and so it should be automatic, right? And this becomes 1 over 4t when I square it. dy dt is equal to 3, and therefore dy dt squared is equal to 9. That means that I have the integral from 0 to 1. I've already been given my alpha and my beta, my limits of integration with respect to t. And this is 9 plus 1 over 4t dt. And of course, it does wind up being 3.249 when you plug it into your calculator. And let's go ahead and verify it again, since this is still a little bit new. We'll verify it by eliminating the parameter. Now t is equal to x squared, and therefore y becomes 3x squared minus 1. Okay, and when t is between 0 and 1, so is its square root. So my limits of integration are now in terms of x, but they look like they didn't change. Okay, well this right here, dy dx, is 6x. So therefore dy dx squared is 36x squared. So my length in terms of my rectangular formula is 0 to 1. Square root of 1 plus 6x squared dx. Now, basically, in order to do this by rectangular, you're going to have to do some trig sub. So if you have tangent theta is equal to 6x, that means secant squared theta d theta is equal to 6 dx, and therefore dx is equal to 1/6 secant squared theta d theta. That means that this is transformed into 1 plus tangent squared theta times 1/6 secant squared theta d theta. Now the only question is, what are the limits of integration? Well, when x is 1, tangent, that means tangent theta, or when x is 0, tangent theta is 0, and tangent theta is 0 at 0. When x is 1, tangent theta is 6. Well, we don't really have a unit circle value for that, so we'll just put arctan of 6 up here, since it actually does stand for a number that will pop out of your calculator. Now, when I simplify this, this obviously becomes secant squared in that radicand. And of course, the square root of secant squared is secant. That combines with this secant squared to become secant cubed, and I have 1/6 from 0 to arctan of 6 of secant cubed theta d theta. And we can go ahead and just put that into our calculator. Okay. We are in parametric. Let's go ahead and do this parametric one by the calculator. I'll show you the work that was done. Remember that we already have it up here, and all we have to do is go back to the main screen and find one that we've done in parametric. Okay, and then we just have to alter the limits of integration if we need to, and in this case we do need to. Okay, actually, yeah, okay. The problem is, of course, the fact that the t is in the denominator right here. That's why it's giving me that error. So I actually remember I had to go and do it by hand instead of by formula on this one, and I did get that. I could probably scroll up and find it for you, but let's not do that right now. Let's actually go to the function, and let's go ahead and just do this one by hand. 1/6 times the integral of 0 to inverse tangent of 6 of 1 over, and this would of course be cosine x cubed dx, and this may take a while. Oh no, actually came out 3.249, and there we go. Okay. Let's go ahead and move on from here. Let's do one more arc length problem. I'm not going to do this one. I'm not going to convert this one to rectangular. I think the reason should be evident. I'm just going to do it. It's long and involved enough in terms of just the parametric. So, first thing, of course, that we need is our dx dt. And that becomes e to the t times sine t, so the derivative of the first times the second, plus the first times the derivative of the second. And we can, of course, simplify this to sine t plus cosine t by factoring out the e to the t. Now, my dy dt is going to be the derivative, or let's do the first, our derivative of the first times the second, plus the derivative of the first, or the first times the derivative of the second. Well, it's going to be minus e to the t sine t, because when you take the derivative of the cosine, it's going to change that sign, S-I-G-N, sine, right? And you get e to the t, and this is cosine t minus sine t. Now, let's go ahead and square them and clean them up before we put them in the radicand in the integrand, okay? And sometimes this is a good idea, sometimes it's not necessary, but this becomes e to the 2t, and then if I FOIL this, I get sine squared t plus 2 sine t cosine t plus cosine squared t. Now, this right here, sine squared and cosine become 1. 2 sine cosine becomes sine of 2t, and therefore you can simplify this as 1 plus sine of 2t. Now, dy dt squared, something similar is going to happen. You get e to the 2t, and then you're going to get cosine squared t minus 2 sine t cosine t plus cosine squared t, and that's going to simplify in a very similar fashion. It's just going to be 1 minus sine of 2t. Now, of course, when you add these together, okay, when you add these together, you're going to get e to the 2t factored out, and you're going to get 1 plus sine 2t, 1 minus sine 2t. And so the sine 2t's are going to cancel. But let's go ahead and just plop it down from 0 to pi. I was given my alpha and my beta, my limits of integration. And you get e to the 2t, 1 plus sine 2t, and then plus e to the 2t, 1 minus sine 2t. And from here, you can probably see that when you factor out that e to the t, when you factor out that e to the 2t, you can simplify it just into e to the t. And then it's 1 plus sine 2t plus 1 minus 2 sine t. That simplifies into radical 2 dt, or rad 2 from 0 to pi of e to the t dt. From here, remember that e to the t integrates as e to the t. And what I get here is rad 2 times e to the pi minus e to the 0, which is just 1. And this actually approximates to 31.312. Okay. And if I went ahead and actually plugged these in, if I went ahead and plugged these into my y equals, I'd have to go back to parametric, of course. And I do the e to the t times sine t, and then e to the t cosine t. Let's go back to our main screen. And basically all we would have to do is integrate this and just change the limit of integration over here to pi. And we get exactly the same thing. Okay, we get exactly the same thing than if I were to take root 2 and then e to the pi minus 1. Same exact value. Okay, so that confirms that, you know, basically all of our hard work here and the algorithm in the calculator are giving us the same answer. So, you know, that should give you warm fuzzies that you're on the right track. All right, the last thing we need to do is we need to do surface area. All right, let's go ahead. Now remember, surface area is related to arc length, and in rectangular, it's the integral from a to b of 2 pi r, which was the length of that rectangle, right? Because it's the idea of the outer rim of a cylinder, if you basically unfold it, winds up being a rectangle. And this right here was the length, because the length of that rectangle basically was the rim that created the circumference, and this was the width of those. Now, that looked a little bit different when it came to rectangular, but again, we need to basically figure out how to represent those in terms of parametric, because it's the same principle, right? Again, we're going to assume that there is an alpha and a beta which correspond to that a and the b. And so we have the alpha and the beta. And you know me, I like to pull my 2 pi out in front. Now the r is again going to be y. And then the arc length is just going to be the parametric version of the arc length. And that should, of course, be no surprise. So that's it. I mean, that really is that simple. So let's go ahead and use that to find the surface area for this one. Surface area of revolution for this one. Now, my dx dt is going to be 3 minus 3t squared. And my dy dt is going to be 6t. So let's go ahead and plug it in. We'll solve. So we get the surface area is 2 pi, and I already have from 0 to 1, right? I've been given my alpha and my beta. And now my y is just here. So it becomes 3t squared. Now I need the radical, which represents the arc length, and that's going to be dx dt, or sorry, that should be squared, and then dy dt squared times dt. Okay, well, I can clean up that a little bit. What I'm going to do is I'm going to go ahead and FOIL this, and then I'm going to multiply that out, and I'm going to see whether there are like terms that collect. And there should be, because the middle term of this one will be a squared term, and it will combine with this one. And you're going to see that it actually combines rather nicely. So we have 0 to 1 of 3t squared, and this becomes 9t to the 4th minus 18t t squared plus 9 plus 36t squared. Now, this right here is a perfect square trinomial. It came from here. What this is going to do is it's going to turn that negative 18 into a positive 18, and we're still going to have a perfect square trinomial. It's just going to be the sum rather than the difference. And we get 9t to the fourth plus 18t squared plus 9 dt. 2 pi from 0 to 1 of 3t squared times the square root of 3t squared plus 3 squared dt. Well, of course, a 3 can be pulled out of here, right? Or actually, I mean, it winds up being a 9 when it gets pulled out. But what I have here is we're going to just go ahead and simplify over the next couple of steps, and we get 3t squared and 3t squared plus 3 dt. Now, there's a 3 in here, there's a 3 here, and there's a 2 pi out here. We're going to combine those, and we're going to get 18 pi. And then I'm going to take this t squared, and I'm going to distribute it across this t squared plus 1. And I'm going to get t to the fourth plus t squared dt. Now, for something that was really, really messy, that wound up cleaning up rather nicely. And so I get 1/5 t to the fifth plus 1/3 t cubed, evaluated from 0 to 1. Now, of course, when you plug in the zeros, you're going to get 0. When you plug in the 1, you're going to get 1/5 plus 1/3. Well, 1/5 is 3/15. That's 5/15. So it winds up being 18 pi times 8/15, which, you know, because there's a common 3 in here, winds up being 48 over 5 pi. And I won't keep you in suspense. That approximates to 30.159. But there is the surface area of revolution. And, you know, again, you could take these, plop them into your x1 and y1 in parametric in the y equals menu, and then basically use, you know, the integral of 2 pi 0 to 1, and then of course it would be y1 times the square root of that x2 squared plus y2 squared, and then just dt. And if you did that on your home screen, as long as you've done everything correct in the y equals menu, you will get exactly that approximation. Okay. Now, let's do one more quick one, and then we actually will be done with these videos. Okay, well, again, this one actually is relatively easy, so let's just do dx dt, and that's going to be t squared. You have dy dt, and that's going to be 1. And so basically what we have here is we have the surface area is 2 pi, 1 to 2, of, then of course we need our y, so t plus 1, and then this winds up being t to the fourth plus 1 dt. And you could probably do this one by hand. Yeah, you would probably have to do it by trig sub. I didn't try to do it by hand. I just went ahead and loaded it into my calculator. And this one actually approximates to 41.701. Okay. And sometimes I'll ask you to basically grind it out, and sometimes it's enough just to see that you've set it up correctly. Because this right here is my y, this right here is my arc length. Okay, and of course my y is also, you know, this is my r in terms of 2 pi r. My arc length, of course, is what I was referring to as my width, because it's rectangular areas that I'm actually summing up. I hope this is helpful. If you have any questions, do shoot me an email. Bye.